So this is Math 1127, Stat and Probability, Session 3.3, the addition rule. Now, the first thing as I want to get through is the definition, mutually exclusive events. So as we talked about before, a probability event is simply something that with a collection of outcome. So some outcome that you want to occur or not to occur. So what is mutually exclusive events? A and B are mutually exclusive events if they do not share any outcomes. So for example, let's just say A is, let's just say, let me see, the Republicans will wins the Senate in 2020, right, for this November election, and B is the Democrats wins the Senate in 2020. Now, as you guys know, who are, you don't have to be well versed in politics to know, only one political party can win the majority within the Senate. So it's either one or the other, right? You could have a 50-50 split, but then a VP, in this case, whoever win the presidency, will be able to kind of tip the balance over, right? So A and B are mutually exclusive because A and B cannot occur at the same time, on the same timeline. They're not going to be able to do that. Now, here's another example. Let's just say A is the Republican wins the White House. So in this case, would be President Trump. B would be the Democrats wins, win. I should say the Republicans win. So more than President Trump has, Mike Pence and all that. The Democrats win the House of Representatives. So can those two happen at the same time? Absolutely. It's actually currently happening right now. A and B are mutually inclusive because both can take place at the same time. No problem. So now let's look at some of the examples in the homework. One event here says, so 3.39, someone who smokes cigar, the other is male. Can those two happen are those two mutually exclusive? Meaning, can you have a male who smokes cigar? Of course. So no, you can smoke. Are those mutually exclusive? No, because someone who smokes cigar, well, actually, right? No, because someone who smokes cigar can be a male. There's no rule saying you cannot be a male and smoke cigar, right? I cannot smoke cigar, right? So check. The other one saying that an animal with green eye and blue eyes. Of course, they are mutually exclusive since you cannot have both at the same time. So pretty easy. A company that makes cotton found the probability of producing cotton with a puncture is 0.06. The probability of a cotton has a smash corner is 0.1. The probability that a cotton has a puncture and has a smash corner is 0.006. So the question here would be, think about this, right? The idea is you have two events. Maybe I should type it up. So the two events that we are talking about here, 3.3.15. Event A is producing a cotton with a puncture. B is producing a cotton with a smashed corner. So first of all, right, can those two happen at the same time? Yeah, sure. Why not, right? So the mutually exclusive thing is no, because you can have both at the same time. You have a puncture and a smash corner. If a quality inspector randomly selects a carton, what is the probability that it can have one of the other? So think about this, right? This is probability of A is 0.06. Probability of B is 0.1. The question is, what are the chances, right? What's the probability that A and B will A or B, I'm sorry, will happen, one or the other. So that's the key, one or the other. That's actually a formula for this thing. So formula for the probability of either A or B or both to happen, right? Is this guy. So let me change that into an equation. Probability of A or B equals fraction probability. Oh, actually, I'm sorry, not fraction. My bad, tripping. It's probability of A. So you look at all the look at the chances of A happening, and then you add the chances of B happening. Makes sense, right? One or the other. So you add the two together. But here's the thing: you have to always subtract the probability that they could happen at the same time. Because if you add A and B, you're actually double counting the probability that both A and B will happen at the same time, since they are included in both A and B. So you have to subtract the probability of A and B happening at the same time. So now it's might be better if I move this to the next line. Okay. So now looking at this guy, right? The probability of these two, let me see. I need to know. So I'm trying to get this to be in here. So this would be the new equation, right? Will be the probability of puncture. Let's call it puncture, and the probability of smashed corner, right? So you got to add those two together. Like that. You don't have to really write that when you're solving this problem. I'm just trying to show you. So of course, in our case, right, this would mean equals 0.06 plus 0.1, right? But now, what is the final one? Puncture and smash. And if you look at the problem here, the probability that a carton has a puncture and a smash corner is 0.006. So maybe I should put it up here. The probability, right? See, this is both. Producing a carton with a puncture and a smash corner. All right, that's C. And that will be, well, actually, it might be more. That's A and B put together. So that will be probability of A and B will equal to 0.006. Right? But it doesn't matter. In the end, you just gotta make sure you subtract 0.006 here in the end. And that will be the answer. What is that? 0.16, 0.154. There you go. So pretty much it's exactly what you think it will be. Just add those two, subtract the common graph. Now, for 3.3317, let's see what's up with this guy. So again, it's a poker card, right? So we have to compute first the probability of obtaining a club or a heart. Again, if you're not very well versed with poker cards, just go on YouTube or something like that and check it out, right? So for poker, compute the probability of a club or a heart if you just randomly draw one card from this stack. So the question would be, how many clubs do we have? Plus, how many hearts do we have? And then you subtract how many are in between, which is club and heart, right? I know for people who play poker, you know what you're talking about, right? Well, here's the thing. How many clubs do we have in a poker deck? 13. How many do we have in a heart? 13. How many hearts do we have? 13. How many are both club and heart at the same time? The answer is none, right? You cannot be both at the same time, right? So just make sure that this whole thing is a fraction and needs to be put over 52 because you got 52 cards, right? So that's 26 over 52 and it's 1/2. Makes sense because think about it, right? That is basically half the deck, right? Club and heart. So that is 0.5. So let's see, B. What is the probability of club or heart or spade? So now that's 3. So, this time we don't have to go crazy, right? Club, heart, spade, that's 13, 13 plus 13. So that's 39 over 52, which is 3/4, which is 0.75. Right. What about 3 or spade now? This one is a tough one. 3 or spade. So that's the probability of drawing a 3 plus the probability of a spade, subtract the probability of both. Now here's the thing. How many 3s do we have? We have 4 in a card, right? So I'm gonna put on parameter because I know what's coming. How many spade? 13. So not too bad. Subtract by what, right? How many 3s with a spade? Well, you have 4 3s, right? A spade, a 3 of spade, 3 of heart, right? You have 4, so you only one of them is with a spade. So that's -1. And that you have to divide it by 52. Basically, you have 4 cards that are 3 and 13 cards that are spade. You add them together, that's 17. But one of those cards, you just double count it because it has both, right? Both sides claim one of those. So that should equal to, what is it, 4, that's 17, that's 16 over 52, right? Which is, let me see, you can divide by 4, right? That's 4 over 13. And let me see, what is that in decimal? 0.308. By the way, those who like poker theory and all on ESPN, that's how they calculate probability of somebody winning. Now the next one, let's see, is the probability. So you're rolling a 6-side die. So the question is, what is the probability of rolling a 4? So the probability of rolling a 4 or a number greater than 3. So think about this, right? Some of them actually mutually exclusive, are mutually, I'm sorry, mutually inclusive, right? Because here's the reason. let me draw the sample space, right? The sample space is 1, 2, 3, 4, 5, 6, right? But here's the deal. 4 is right here. That's 4. Greater than 3 is 4, 5, and 6. Like this. So greater than 3 already kind of covered 4, right? So regardless, it's still 3 out of 6, which is half. So yeah, you know, it's kind of stupid, but basically they try to get you to see that, right? There you go. Now, next problem. What is the probability of rolling a number less than 4 or an even number? Okay, now we're talking. So let's call back that sample space here. So let's see. Less than 4 means these 3 guys, right? 1, 2, and 3, right? Or even. Well, 2 is even. We already highlighted. But 4 and 6 are also even. So we end up with 5 out of 6. And what is that equal to? 0.833. Then the next one is the probability of 2 or 1 or 3 or 5. And again, it's just think about, right, from the sample space perspective, you just have to highlight those guys, right? 5, 3, 2, 1. Look at that. So that's 4 out of 6, which is 2 over 3, which is equal to 0.667. So not too bad, Just kind of a little bit weird when you read the problem. There you go. So now, is this mutually exclusive? No. Why is it? Because they have something in common, right? It's like somebody being a nurse, somebody being a male. There are people who are male nurse right in the middle. Done. So let's see, is this, well, we already answered that, so I don't know why they give you the same question, right? These are pretty easy. So, percent distribution of live multiple delivery, 15 to 54 years old, find each probability. So it's pretty easy. You just look at like probability of 30 to 39. Just look at the picture. 24.7%. So the first one is not bad. You just gotta wait a minute. Oh, actually, my bad. I'm blind. So 30 is right here, right? 37.3%. 35 to 39% is 27.7, 24.7. You just have to add those two together. Add those two rows together. So that's 37.3 plus 24.7. So that's 62%. Just like, what's going on here? Oh, my bad. 0.62. Right, because 62% is 0.62, right? And then what about people who are not between 30 and 34, 39 years old? Well, think about this. Let me type this up. Here's the thing. The probability of not something, say not A, isn't that equal to 100% minus the probability of that? I mean, think about it, right? If you have a quarter chance, we have a 25% chances of getting a promotion. Well, then you have a 75% of not getting it, right? How do you get 75%? You subtract from 100%. So really, this is just 1 minus probability of A, right? Because 100% is 1, right? So look at this guy. If that is 0.64, just do this. 1 minus 0.64, that's 0.38. And that makes up 100%. Right? That's all that is. So, and less than 45, let's just look at the graph, right? 45 is here, right? So that's 3.8%. You want everybody except for that 3.8%. So that would be 0.0 let me see, 962. There you go. So basically 1 minus that. At least 20, what does that mean? Well, 20 will be starting from here, right? 6.2%. At least 20, that means from here all the way to the top. So you are excluding the 1.2%. So there will be 0.988. Right, there you go. This is the same thing. Just read the problem, you'll be fine. Same thing over here. Just read the problem. I mean, probability of frequently involved or being occasionally involved, right? Frequently involved, that's 628. Occasionally involved is this. Add those two together, right? Just like what we did before, right? Let me just do one. So 428 plus 882, right? Divided by the total, 2851. So that's 0.459. Like that. Okay. So nothing to it, just it's gotta be careful. So, and again, if you have any question, man, just give me an email, give me a text message. This session shouldn't be too bad. So, all right, well, that's the end of session. Thank you for your attention.